Have you ever been puzzled by unexpected results in your code? It can be incredibly frustrating, especially when you're working on something as complex as a multi-threaded application. If that sounds like you, stick around because today we're diving into a common issue in Java multi-threading. I totally understand how disheartening it is when your code doesn't behave as expected. You're not alone in this. Many developers face similar challenges when dealing with concurrency. It's one of the trickiest aspects of programming. Let's take a closer look at the specific issue at hand. One user recently reported that while running a loop to increment a variable in a multi-threaded environment, they were getting unexpected values. They expected the variable to equal 100,000 after the loop, but the output was much higher. Sound familiar? Let's explore this together. So, what could be causing this unexpected behavior? In multi-threaded applications, race conditions can occur when multiple threads access shared data simultaneously. This can lead to inconsistent results, especially when incrementing a variable rapidly. And don't go anywhere. At the end of this video, I will share a crucial tip to help you avoid these issues in the future. To address the unexpected results in the user's multi-threaded application, we first need to understand the behavior of the atomic integer and the concurrent hash map. The user is using these classes correctly, but there are some nuances to consider. Next, the user should ensure that the increment operation on the atomic integer is synchronized properly across all threads. Although atomic integer is thread safe, the way the value is stored in the hash map can lead to race conditions. To fix this, the user can modify the code to use a synchronized block when updating the hash map. This will ensure that only one thread can update the map at a time, preventing unexpected values. Additionally, the user should consider using a thread-safe collection like concurrent hash map for storing the incremented values. This will help manage concurrent updates more effectively. Finally, the user should test the application again after making these changes. They should observe the output to ensure that the value of the variable does not exceed the expected count. Fun fact: did you know that the term race condition comes from the idea that multiple threads are racing to access shared data? It's a race you definitely don't want to lose. Now, let's look at the answers provided by other users. An alternative solution points out two defects in the demo program. The first issue is with the way the loop is structured. Even after fixing the initial problem, the final value of the variable can still exceed 100,000. This user tested the program with multiple threads and observed that the final values were consistently higher than expected. The user explains that when the loop reaches its last iteration, all threads see that the condition is still true, allowing them to execute one more increment. This happens because the increment operation occurs after the condition check, leading to unexpected results. Now let's see a response from a different user. The user points out that every time a new thread enters the run method, it resets the count of I to 0. This happens because of the statement i.set0 at the start of the loop. They also highlight that after fixing the reset issue, it's important to analyze how the threads behave. For instance, if 3 threads enter the loop while a fourth increments I, value to be incremented stored could increment multiple times while I only increments once. Here's the tip I promised. Always use thread-safe collections when working with multi-threaded applications. This simple habit can save you from a lot of headaches down the road. And there you have it. By understanding race conditions and using thread-safe collections, you can avoid unexpected results in your multi-threaded applications. If you found this video helpful, please subscribe for more tips and remember to keep coding confidently.